G'day folks. Well, here's a fascinating little device for all you lovers of things novel. It's a magnetic levitator, or a device for suspending something in mid-air like that. Now how it works is that there's an electromagnet up here and an infrared beam from here across to here, so we can sense the position of this. And inside the bobbin here we've got a super magnet. In fact, there's two in there. Two of those neodymium super magnets, so that the electromagnet here can attract it and suspend it. And of course, when it goes up, it'll cut the infrared beam, and it sends a signal from the photodiode down to a microcontroller, and that adjusts the pulse width modulation sent to the coil up here and adjusts the attraction. So it works quite well, but it's taken a while to develop. We had instability issues initially, and taken a while to work through them. I saw a bit of advice once that if you're thinking of making one of these things, make everything adjustable, and that's pretty darn true. Okay, so the whole thing's pretty much 3D printed. These are 3D printed. The coil form is 3D printed. The wires come from a transformer out of an old microwave oven. These brackets here are 3D printed. The case is off the shelf. And if you look in here, we can see the infrared sensors here. You may just be able to see them shining. I don't think you can. But anyway, there's 8 3mm LEDs in there, infrared, and there's a photodiode here, an infrared photodiode, which senses the intensity of the light coming from these LEDs. And as this comes up, of course, it cuts the beam, sends a signal to that, which then the Arduino Nano microcontroller here senses, and it adjusts the current in the coil via the MOSFET driver here. That's just a little power supply, and that is a constant current supply for the LEDs here. It is adjustable for the reason that we don't want to swamp the photodiode here. So we adjust the current through the LEDs so that it's operating in the linear portion of the range here. And it works quite well, as you can see. Very fascinating, I think. Just sitting there like that, it's drawing about 200 milliamps, 0.2 of an amp. But you can, if I pull it down, it senses that it's low and applies more power to the solenoid, and you can see the current going up. Now the coil resistance is about 9 ohms, so it can potentially draw an amp. And written a sketch so that if it senses that there's no bobbin in there, it will shut the current down. Just in case this falls down and I'm not here, it's not going to burn the coil out, it will shut down. So that was a useful little feature. Now, talking about instability issues, anyone who's had anything to do with servo systems will probably understand the P.I.D principle of servos. It's proportional, integral and derivative. Now in the sketch here I've implemented proportional and derivative. I haven't worried about the integral part of it. Proportional just means that the power to the solenoid is proportional to the error sensed by the photodiode here. Obviously there's a range of voltages coming from this, from 0, when there's no, when the infrared is totally blocked, to about 900 coming when there's full light. And the set point is halfway between those two, so about 450. So what do these numbers mean? Well, it's the analog to digital converter in the Arduino Nano is a 10-bit conversion, so it's capable of producing numbers from 0 to 1023. So half of that's about 450. So that's the set point. Now anything lower than the position lower than the set point will generate an error. An error is the difference between the sensed position and the halfway position, and that will then get converted to pulse width modulation drive for the solenoid. Just with proportional on its own, you get instability. It overshoots, undershoots, and will eventually just fall out or slam up into the iron core. So the way around that is to introduce derivative action, and all the derivative action does is look at the velocity of the bobbin, the rate at which it's moving up or down, and that's converted to a negative signal which is added to the proportional. So it tries to dampen any vertical movement. So it's actually P.I.D, acronym for proportional derivative action, and it works really well, but it's a very delicate balance between position here, position of the emitter and sensor, and adjustment of the proportional and derivative constants, and a small delay in the sketch loop. So it's quite a delicate balance, but it does work really well. Anyway, I hope you enjoyed that, folks, and thanks for watching.